I guess I'm introducing Jacob. Jacob was a student, I think 3 of my classes, I believe. One of which I actually got to see him for a few weeks into the abandoned campus. But in one of them, I didn't even know he was there. He never turned on his camera. I never even knew he was in that. And later he told me he was one of the students. Jacob asked, he wanted to talk to me about doing a project, capstone project. So I asked him, well, what do you want to do? He said, I want to be an engineer. So you should think of that during the whole talk. He wants to be an engineer. And I said, well, what about that? And he said he likes to build things. And I said, well, okay, what have you built? And amazingly, he took his computer and he sort of turned it around his room. There's a robot arm over here. There was an Arduino over here. And so I'm thinking, yeah, you should be an engineer, really. So we had to it took us a couple of weeks. We had to come up with a topic that an undergraduate could build. So he's not going to build a space telescope or something like that. We need something an undergraduate can build, but it's somewhat challenging. And there's several of us in this room who have taught undergraduate mechanics. And we know this topic, which is rigid body rotation, is something we tread very carefully in with our undergraduates. It's a topic that's sort of a dark corner of undergraduate physics because it's not obvious. It's like everything we've taught them, we suddenly now tell them that rotating bodies don't quite do what we've normally done. So I figured that was a good topic, and I think he did a good job. He didn't have a lot of time, but he built something, and he's going to explain the strange world of gyroscopes.
Thank you, Dr. Jones. So, as was stated, I'm Jacob Watkins, my advisor, Dr. Jones, and my project, the physics of gyroscopes and their applications. So, for this presentation, we'll be talking about what is a gyroscope, what are its properties, and the construction of a gyroscope, more specifically, how I constructed mine. So, first off, what is a gyroscope? A gyroscope is a rotating rigid body of mass. The axis of the body's rotation also should pass through its center of mass, and the body should be symmetric about that axis. It's usually a spinning disk, but it does not have to be. A common example is a top, which I'm sure you've all seen. So, properties of a gyroscope. They have a large angular momentum, which gives it its fixed orientation. They obey the counterintuitive right-hand rule, and they precess around their original axis of rotation. An example of this fixed orientation is the Foucault gyroscope. A Foucault gyroscope is one that has a free axis of rotation about the north-south meridian with its spin axis perpendicular to the meridian, in this case pointing towards, let me use the laser, pointing towards the sun. To an earthbound observer pictured here, it appears that the axis rotates 360 degrees every 24 hours, when in reality it is the observer experiencing the rotation of the Earth. Okay. Torque. Torque is an idea that is critical to understanding gyroscopes. So what is it? It is the ability of an object, or ability of a force to cause an angular acceleration upon an object. If you understand how to open a door effectively, then you already understand torque. So how do we open a door optimally? Well, you push with a perpendicular force as far away from the hinge as possible. We can imagine trying to open a door by pushing directly towards it, but nothing would happen. We intuitively know it to be true, and if you look at our torque formula over there, you'll see sine theta with theta 180 in that case, which would give us a torque value of 0. When there is torque, however, how do we find its direction? We find it using the right-hand rule. So I need everyone to raise up their right hands. We'll go over this. So the first thing you're going to do is align your palm with the axis of rotation. Then you're going to point your finger, let me get over here. You're going to point your finger towards the force, where the force is being put onto the object. Next, you're going to align your middle finger with the direction of the force, and then you're going to stick out your thumb. Your thumb, in this case, indicating the direction of the torque vector. Congratulations, you now all understand the right-hand rule. Here we graduate from a simple line of a hinge to a disc. Instead of using the two fingers, you simply just wrap your hand in the direction of rotation, and your thumb indicates the angular momentum vector. Over here we go over what happens when a force is applied on a separate axis of rotation. So up here we have a counterclockwise spinning disc, much like the one over there. And here, a downward force is applied in the front and an upward force in the back, which can be imagined as pulling the angular momentum vector out of the screen like a lever. And what happens? It tilts down and to the right. That's weird. So let me give a more intuitive explanation. If we imagine an object moving directly to the right with an initial velocity, it then comes into an upward force. Afterwards, it has a velocity going up and to the right, not straight up, not straight to the right, kind of a combination. So if we take our disk example and instead imagine it as an object in orbit around this dashed line, a downward force hits it here, which then knocks it off its path. It wraps round, through again, and back to the point of collision. And if you then view that orbit as a disk, you'll see it tilts down and to the right. So when you pull this axis out of the screen like a lever, it tilts down to the right, obeying our right-hand rule. An example of this in the real world is a helicopter. A helicopter has its main rotor as its source of lift, which also allows it to fly through the air at significant speed. The main rotor is also used to go forward and backward as well as side to side. It does this by tilting the rotor in the direction it would like to go. In this case, we're going to say it wants to go forward. For that to happen, there needs to be a downward movement at B and an upward movement at D. And the blades, by the way, are spinning counterclockwise. So where do the forces need to be applied? Well, for a downward movement to occur at B, a downward force needs to be applied at A, 90 degrees ahead of where the movement actually occurs. And for an upward movement down here at D, an upward force needs to be applied at C, again, 90 degrees ahead. This will then result in the disk tilting forward, allowing the helicopter to move forward. Okay, now that we've all gotten the necessary physics out of the way, we can go to how I constructed my gyroscope. There are three main aspects: the mechanical, the electrical, and the gimbal. The first thing I did was look at how other people had created their own gyroscopes. I found that most started with a hard disk drive, so I decided to do the same. I obtained 10 hard drives and scavenged these for parts, which were a suitable motor and platters being these metal discs you see here. I put as many platters as I could fit onto my suitable motor to maximize the mass and therefore the gyroscopic effects. Although this seemed like a great idea at the time, it wasn't. It came back to bite me later, and we will talk about that later. So the controller. I need to find a controller that can communicate with a 4-port brushless 3-phase DC motor. Luckily, I was able to find a 5-volt to 12-volt DC motor controller offered by a US seller. Before I could get it, or before I could install it, I had to find the COM or ground port of the motor, which could be easily accomplished using a multimeter and testing the resistance between each of the 4 ports and seeing which one had the lowest. It turned out to be that one right there. Once I knew that, I was able to hook it up to the controller, hook a power supply up to the controller as well. So the motor and the controller were connected here and the power supply there. And then test it. And it worked. So that allowed me to move on to the next step, which was putting everything together, the unification. The first thing I did here was attach the controller to the body of the gyroscope. I did this using double-sided adhesive tape, making sure to leave easy access to the resistance dial there, which acted as a throttle for how much power you're giving the motor. I then wired the power through and around to the battery, which would be mounted in this 3D printed mount I put here. And yeah. I then tested it and it still worked. So I moved on to the next step, which was the creation of the gimbal. This was probably the easiest step of construction. I really just went to Home Depot, bought wood, mending plates, and some screw eyes, and put them all together to see for this masterpiece you guys see here. The main point of the gimbal was to mount a gyroscope in it, which I did by supergluing these mini beams to the side, which then allowed proper demonstration of the ideas we covered in the physics portion of this. So the first demo here shows a gyroscope. The effects of gravity are trying to tilt it down, trying to bring it flat. However, as we learned through the right-hand rule, it's redirecting that force, or it's, well, kind of creating its own force that goes perpendicular to that force, keeping it up and making sure it doesn't fall. This next one here is pretty much, or it is exactly what I talked about with the helicopter. It's spinning counterclockwise. I put an upward force here, and what happens? It spins, goes up like that. So the back comes up, again, 90 degrees ahead. So then what happens when I put an upward force here? The part facing us goes up. 90 degrees after the force is inputted, you see the movement. So yeah, and for those with keen eyes, you might notice this is a different gyroscope than the one I've shown previously. That is because, for those of you who are in the class where it happened, this demonstration puts a lot of torque on the motor, the internal motor. And when I had all that mass on the motor, what happened was the torque was too much and it kind of just tore it apart from the inside. Makes a disgusting sound when it works now, so I just made a new one. Yeah. So what was my purpose? As Dr. Jones stated, I'm going to pursue a career as an engineer after college. And I wanted this to be a multidiscipline project that included physics, mechanical engineering, electrical engineering, and we came up with this. And I think that it covered what what I wanted to do, more so what I wanted to prove, most importantly to myself, so that I could be an engineer. Yeah, I think I've accomplished that. Before we get to questions, I just want to say thank you to everyone, specifically my parents and Dr. Jones, as well as all the students who did their capstones with me. You guys really inspired me, and of course, the teachers as well. Thank you.
Any questions? So you're planning on staying in the area and applying for jobs here?
No.
Or?
I'm going back home to San Diego.
Cool.
So I'll be looking at jobs there. So
Could you provide an explanation as to why the bike wheels on a car spin when the car is moving? Like if there's a bike rack.
Oh, I think that's more wind. At least that, yeah, because I don't think that's would be any gyroscopic effect. I think it's just interacting with the wind. So. Yeah.
Will you be doing a demonstration of how your gyroscope works on this?
Oh yes, of course. I brought my gyroscopes, and since I'm last, if any of you guys would like to see them, I can show afterwards. To put me on the spot. I mean, like, you know, once everyone's like walking around.
We should say that the real-time failure of your demonstration in the dress rehearsal was one of the funniest things I've seen in my life. It was comedy gold.